The analogy is that we said here is that Rutherford's model, maybe I should say planetary model, is a bad model. Is a bad model of the atom. So when I think about this, I have some nuclei. And we know that the nuclei is positive. And in this model, we know that we have an electron. And this electron is whizzing around in a planetary orbit. We know that this is a bad model. In a very analogous way, in nuclear physics, there is another bad model of the nucleus. Okay, and what I mean by that is that the depiction we have of the nucleus, and by the way, I perpetuated it, and I'm not even sure if I'm even going to address this issue here in this course, because why? It gets complicated very, very quickly. So if you see a picture of a nuclei, let's say that looks like this, or these are the protons, these are the neutrons in here, right? So in this case here, I'm going to say that, yep, here's a neutron, and then here is my proton. So this is what I would call a proton. This is what I would call a neutron. If you see this image of the model of a proton, guess what? It's not very good. It's a terrible model. And just to show you what I'm talking about, all I did here was do what? Let me go share my screen with you so you could just see. Look at this. I just typed in nucleus of atom, and look at all these pictures that they're showing of the nucleus. That's my point. It is not a good model. And the question is, you might ask the question, so why are you teaching me this if, it's a bad model? Well, here's what we know. Neutrons and protons. So what we know here is that neutrons and protons in the nucleus have a shell model. And this model's more complicated than it was for electrons. Furthermore, these neutrons and protons can change into each other. As a consequence, just having this picture like this doesn't do it any justice. But that's what we got to deal with for right now. We could still learn a lot about it, and we will. So let's keep moving on here. So when you look at this picture here, and here's another reason why this model is not so good, and probably the biggest reason. This model of the nucleus is missing something big. And the reason why that is just so just, let's say, by looking at the electric forces of the proton, there is a big problem. And the big problem is it shouldn't exist. Okay, it shouldn't exist. Right? So when I'm looking at this, it shouldn't exist. So if I think about this, let's take this image of our bad nuclei model. And when you look at this thing here, look what's actually happening. There's electrical repulsion. In fact, as this thing gets quite large, that means the nuclei gets quite large, you find that the electrical force is trying to blow the nucleus apart. So what we're saying here is that there is a huge electrical repulsion inside the nucleus by the protons. So what you're seeing here is that the electrical forces, which I'm going to call E forces, the electrical forces are trying to blow apart the nucleus. So the question is, what's going on? Now we know that many nuclei are stable. And remember what we mean by stable. Stable means at least one stable isotope, at least one stable isotope lives forever. And as far as, you know, most of the atoms have stable isotopes. And so what I'm really saying here is that if I look at atoms 1 through 82, so this guy's what? Hydrogen. This guy's lead. Most of these have, all of these have at least one isotope. Many of these have multiple isotopes that live forever. So atoms 1 through 82 are stable and not radioactive. So then it begs the question, why is the nucleus not blowing apart? And the answer is that there must be another type of force. that prevents this from happening. Right? There must be something else. And this is where we go to the next piece.